In this video, research on unsintered Karma filter for state estimation and optimal control of chaotic financial model is presented. This video consists of the introduction, problem statement, unsintered Karma filter approach, simulation result, and conclusion. First of all, financial stability is very important as a stable financial system is able to promote economic growth. In real life, the economic factors have undesirable changes such as financial crisis and environment changes that may drastically affect the economy. Financial crisis is a type of chaotic phenomenon. The existence of the chaotic phenomenon in real life financial system may lead to destabilizations of economic. A chaotic behavior review in financial system is due to the unpredictable nonlinear factors. Thus, the formulation of mathematical model is required to solve the stochastic optimal control problem by eliminating chaos and controlling the system. A dynamic model of finance that composed of three first-order differential equations is presented as chaotic financial model. The model describes the time variations of three state variables which are interest rate, investment demand, and price index. The parameter value A represents household saving amount, B is investment cost, while C is elasticity of demand in commercial market. The phase diagram of the chaotic financial model is shown in the following graph. The diagram indicated that the trajectory of the model is a chaotic attractor. Since the model describes the interaction among the three financial factors, the complicated behavior of the model implies that the interplay between these financial factors causes complex behavior. Thus, in order to solve the chaotic behavior, the state equation is formed by imposing the control input to the dynamic model where the function x is the planned dynamic given by the model equation. In presence of the non-random disturbance, process noise is added to the state equation while measurement noise is added to the output equation. Both process and measurement noise are Gaussian white noise sequence with zero means. The initial state is a random vector which is expected mean and state error covariance matrix are given as follows. It assumes that the initial state, process noise, and measurement noise are statistically independent. The aim is to find a set of optimal control sequences such that the cost function is minimized over the dynamical system, in which the expectation cost function is the total of terminal cost function and operating cost function. Therefore, this problem is referred to as the discrete time nonlinear stochastic optimal control problem for chaotic financial model. There are four steps in implementation of unsintered Karma filter UKF. First, obtain the predicted mean and covariance of the state, then calculate the sigma point. Next, calculate the time update and measurement update equation. The concept of UKF is applying the unsintered transform UT to produce estimate using transform sigma point and approximate the mean and covariance. First, we assume that the n-dimensional random state vector X has mean and covariance. On this basis, a set of sigma point is denoted and the component of sigma point metric is defined for I equal to 1 to n using the equation given and the weight of sigma point for I equal to 1 to 2n which satisfy the condition in which the weight value equal to 1. Beta is greater or equal to 0 and beta equal to 2 is the optimal value for Gaussian distribution. Lambda is a scaling factor where alpha determines the spread of the sigma point around mean value. N is the dimension of state vector and chi is a secondary scaling factor which is usually set to 0. Unsintered transform is applied by propagating each sigma point through the nonlinear function hash to obtain transform sigma point. The mean is approximated using a weighted sample mean of the transform sigma point, while the covariance is approximated using a weighted sample covariance of the transform sigma point. We estimate the state by considering the initial value of the predicted mean and covariance of the state, and the sigma point is provided using a priori mean and covariance of the state. Next, the time update equation is calculated using the following equation where the estimated state mean and estimated state error covariance is obtained. The last step of state estimation is calculate the measurement update equation using the following equation where the estimated observation and observation error covariance is obtained. The predicted state mean is updated with updated state error covariance, where the Karma filter gain is calculated by using the cross correlation metric and the transpose of the observation error covariance. For measurable purpose, the cost function is written in its expectation form. Then define the Hamiltonian function, and the augmented cost function is written as the following equation. According to the Lagrave multiplier theory, at a constraint minimum, this increment should be 0. Hence, these necessary conditions, which are stationary condition, state equation, cost state equation, and boundary conditions, are derived. Assume that the cost function can be approximated into a quadratic criteria where Q and R are the weighting matrices. Hence, the optimality conditions are derived as follows with the Jacobian metric A and B. Suppose the cost state equation has the following solution, and consider this solution in the optimality condition. After doing some algebra manipulation, the linear feedback control law is designed as follows with Karma filter gain and radical solution shown. For illustration, we consider the following parameter in the dynamic model with the following initial condition. The coefficient and weighting metrics are as shown, and the sampling time is set to 0.1 second. The optimal cost obtained is 9.5 unit with very small value of sum square error SSE and mean square error MSE. The following figure shows the output trajectory of the model. You can see that the estimated output trajectory could track the dynamic of the real output trajectory accurately. From the output trajectory, we can conclude that the interest rate is not larger than 0.4% and will be reduced to negative 0.2%. The next figure shows the behavior of interest rate, investment demand, price index, and their respective estimates. The trajectory of the state estimate in interest rate seem well predicted the real state trajectory. The state estimates of investment demand and price index are less accurate, but they are still estimating the dynamic of the real state trajectories in the acceptable mean propagation. The control trajectory is added to the dynamical system for controlling the state dynamic that are disturbed by random noise. The figure shows that the first control trajectory starts from 0.35 unit and reduce gradually to the value 0 for controlling the function u1, while the third control trajectory is moving slowly towards 0 from 0.35 unit in controlling the function u3. Here, the most control effort is needed to control the function u2 as indicated by the increment of the second control trajectory from negative 2.2 unit to 0. This figure shows the stationary condition for the problem. The trajectory in the figure verifies that the solution for state estimate and output estimate are optimal. The cost function of 9.5 unit in the UKF approved are definitely the minimum. In conclusion, the unsintered Karma filter approach was applied to solve the stochastic optimal control of the chaotic financial system. The state feedback control law was designed to determine the optimal solution of the system, and the simulation result shows that the system was under control within the time interval given. The efficiency of the approach used is validated. These are the team members that contributed to this project. That's the end of the video. Thanks for watching.